This is our Earth in the middle, surrounded by a bunch of moons and satellites flying around it. Now, what will happen if we accelerate this a little bit? And yes, you guessed it, things will start going wrong. Things will smack into each other. They'll initiate what's called a chain reaction. Fragments will fly into other fragments and will eventually destroy everything in the orbit around our planet. Some of these fragments will even collide with us, causing some serious damage. Now, is this possible in real life? Will this actually occur with our satellites that are in space right now? Currently, we have over 2,000 objects flying around our planet. Will they actually collide into each other? Will this be a reality at some point? This is something called Kessler Syndrome or Kessler Effect, and this is also the basis for the movie Gravity, where Sandra Bullock has to survive in space when things like that occur. Now let's do a little bit of science and math and find out if this is real and if this is possible. Welcome to What the Math. Now, obviously, the satellites we have flying around our planet are not as massive as the moons you've just witnessed. They're more like this. They're size of, let's just say, New Horizons, which is really tiny in comparison. There it is. There it goes flying around. So, if I were to place a bunch of these around our planet, well, we could just wait and see if they actually start colliding with each other and if they initiate this type of reaction, chain reaction as well. But I thought that was not as much fun and also not as realistic because the thing about the human-made objects in this game is that if you were to zoom in on this object, which is right here, and if you were to actually collide something with it, it wouldn't really do anything. It wouldn't turn into fragments. It would not actually turn into anything significant. So, like right here, if I were to smack this, boom, nothing really happens. Boom, boom again. See, it doesn't really do anything. So we need to solve this problem. We need to change something. And I found a perfect solution. So what we have here is we have a tiny object, which is obviously our, satellite flying around Earth. And as I mentioned, there's about 2,000, actually over 2,000 objects flying in space right now around our planet. And of course, we have a very massive object, which is our planet in the middle. So how can we simulate this? Yes, that's right, you guessed it. We're going to place a massive, supermassive, ultramassive black hole right in the middle, and then we're going to fly objects around it that do fragment and do create interesting effects. So specifically, I'm going to be using, let's just see. Let's use Pluto. Why not? Pluto is awesome. It's beautiful. We've just learned a lot of new things about it, and this is going to be our new satellite. So here comes Pluto number 1. It is going to be flying really fast. Alright, so Pluto is right there. This is our first satellite in orbit around the black hole that we're going to name. Let's name it what we're testing. We're testing the so-called Kessler Effect. This is named after Dr. Donald Kessler of NASA, a NASA scientist who actually came up with this idea that at some point when we have really many satellites in orbit around our planet, at some point they will reach a mass or a density, that is, when I say density, I mean number of satellites per volume. That will become really dangerous. So if one of them collides with another, they will initiate a reaction where many different satellites will be destroyed by the resulting fragments. This is essentially what you see in the movie Gravity. Now, what we're gonna do right now, we're gonna launch Plutos. Launch Plutos, a lot of Plutos, everywhere Pluto. Everyone gets a Pluto. Pick a Pluto, that's your Pluto. I'm also gonna launch them in different types of orbits by basically changing inclinations a little bit, because we want to have as many Plutos as possible, right? And I'm going to disable the trails so that you can actually see them better. And here you go, so many Plutos. Look at all these Plutos. Now, I don't know if I'll be able to do 2,000 because my computer will probably not be able to handle that many, but I can do a few hundreds. I can definitely do a few hundreds, and then we can just kind of imagine that this is 2,000s. Now, he didn't really mention how many satellites you need to have before Kessler Effect becomes a danger and reality, but today NASA has a few precautions because there's quite a few satellites that might cause serious destruction. There's actually one from European Space Agency, and their satellite is called ENVISAT. It was only launched in 2002, so maybe less than a decade ago when I'm making this video. And this satellite unfortunately went down in 2012. It didn't go down, it just stopped working. And that satellite, when it orbits, it approaches 2 other objects within 200 meters. So at some point within the next 100 or so years, it's very likely that it might actually crash into them. Now, what will happen if they do crash, and what will happen if a collision occurs? So we're going to keep launching these satellites everywhere. And I don't know how many we have now, but quite a lot. There's probably over 100 now. And as you can see, so far, no collisions. You'll see the collisions when they occur because they'll just be pretty. And actually, just to make this, make them a little bit more, what's the word I'm looking for here? More obvious. I'm going to go in the simulation here, and right on top where it says pause on collisions. Let's turn this on. Pause on collisions. There we go. So now, wait, where did my Bluetooth go? Oh, I turned on chart by accident. There, that's why. Now, whenever collision occurs, the game will pause, and we can then zoom in and check it out in more detail. Until then, let's just enjoy the show. So let's put more satellites in all kinds of orbits. Then we're gonna designate a geostationary orbit right here. This is our GPS satellites. So NASA has finally launched GPS satellites. There they go. All these Plutos right here are the GPS satellites. There's so many of them because that's where geostationary orbit is. So there you go. Now, Roscosmos decided to launch their own geostationary satellite. And I believe the word for them is, I totally don't remember. It's not called GPS, it's called something else. And of course, China decided to launch their own. And so did India. There we go. So many now. So this is looking a little bit more realistic now. There's actually a lot more in orbits, in polar orbits. There's a lot more in more inclined orbits. Specifically, there's a common orbit called Molniya orbit, which is used by the Russian satellites because Russia is mostly in the northern hemisphere. So for them, it's more beneficial to launch a satellite that is uses a very kind of elongated orbit, so that, alright, it's really hard to explain, but it basically looks like this. So it spends a very, very little time on the southern hemisphere, but it spends a very, very long time on the northern hemisphere because they want to get as much communication from the northern hemisphere, but not from the southern hemisphere, because that's where Russia is. In maybe one of the future videos, I'll try to explain this in a little bit more visually, in a little bit more detail, and why it's actually a lot better than using geostationary orbit for Russian satellites. But so here we go. This is quite a lot of satellites I have right now. I don't even know how many, but definitely more than 100, probably 200. So if I were to just kind of run this, for a few, and this is only hours, right? The reason why we chose the black hole, very massive black hole, and Plutos is because they will basically represent sort of like accelerated time here. So maybe one day, one real day of orbit of a satellite on our planet would equal like an hour here. So it's a lot more efficient, a lot faster. So there they go, flying around and doing their own little dance. And because they're so tiny in comparison to the black hole, their own interactions, their own gravitational interactions, are just as realistic as they would be in flying around our planet. So if the collision occurs, it's probably because they've attracted each other over time. Now it's really interesting that today NASA and European Space Agency and also Roscosmos have very, very strict regulations for new satellites. So a satellite has to be able to, after it ends its own life, or after it expires basically, has to be able to reach something called the, I believe it's called a cemetery orbit or a graveyard orbit, where basically all of the satellites go to die. And now this orbit it's a very specific location for depending on where you are. As a satellite, that is, and it's usually where many satellites just kind of spend the rest of their lives. Now, it's still not perfect. It's not a perfect solution to the overcrowding that is happening in around our orbit, around the low Earth orbit and basically the area where all of the satellites are. But it's a solution that is quite good for now. It's definitely a lot safer to have them orbit in the same sort of region of space than have them fly everywhere. So there's quite a lot of satellites that may collide at some point, but let's actually see what happens when a collision occurs. So, so far, as you can see, no collisions. It's pretty safe, nothing's happening. They all have perfectly well-balanced orbits. And so far, Kessler effect is not really occurring. Now, what would happen if I were to add something a little bit more massive? Let's just say this is like International Space Station or some really massive satellite, or some kind of an object that starts to kind of change things a little bit. Or this could also be just the fact that sometimes solar flares and solar radiation can also change the orbit of a satellite. So let's add something a little bit pretty and massive. So I'm gonna go in here, I'm gonna add one of my most favorite objects, Wolf 359. Wolf 359, if you didn't know, is it's a, I don't want to call it a failure, but it's a non-star. It's something that was supposed to be a star but never really became one. I'm gonna place a bunch of them everywhere to simulate the different gravitational disturbances, different objects in space that may disturb other satellites' orbits. And I'm also going to place one flying this way and then another one flying this way. Now, a Wolf, if I were to zoom in on it, you'll see that it's bright because it's a gas giant that is very massive that almost became a star, but just didn't have enough mass to become one. And so now we have these wolves that will cause all kinds of gravitational disturbance in our, I guess we can call it Kessler system, but it's really Earth. So let's see what happens. Now, just watch the days here. It's 1.7 days after the start of the simulation. And I'm also going to actually go here and disable if there's any fragments and dust and particles flying around. We want to make sure that there's nothing so that this is as fast as possible. And so, yes, let's just wait and see what happens. So now what's happening here is that we've basically introduced a random gravitational occurrences that are real. They do occur in space. So like I said, there's things like the fact that there's a little bit of atmosphere everywhere, even around Earth, where it should be really space, but there's still some residual atmosphere. So when a satellite orbits at an altitude of approximately 500 kilometers, it will still get some slowdowns from the fact that there's a little bit of atmosphere. So this is kind of simulated by the introduction of these very, very massive objects that will now fly around with our Plutos. And while we were waiting for something to occur, and maybe nothing will happen at all, while we're waiting for this, let's just talk about why Kessler effect is or can be a problem. So specifically, it can be a problem because of something called domino effect. So if one collision occurs, it will create many fragments, and those fragments will collide with other satellites and create even more fragments. Now, that's obviously what you see in the movie called Gravity. And that can be a problem, of course, but at the same time, in one of the previous videos, I talked about the distances that are, in space, basically. Distance from our sun to Alpha Centauri is ridiculously large, which is why when we meet Andromeda Galaxy, the collision is very unlikely to occur, and it's kind of similar to here. Like, if I were to zoom in on Pluto, it's actually really far away from that wolf. It's really, really far. It doesn't look like it's far, but it's really far. That's why the collisions are not really occurring yet. And it's kind of similar to what's happening in the space around our planet. It may not seem like a lot of space between the satellites, but it's actually, the distances are so large that statistically, if one collision occurs, it's very unlikely that those fragments will cause so-called domino effect. Now, I'm just going to accelerate this just so the time flies a little bit faster until the collision actually does occur. And after 4.21 days, we have our first explosion right here. We're gonna zoom in on it, decelerate our time, and essentially, this is our first collision. So you can see Pluto, I think it's Pluto. Was it Pluto? Something collided into something. Anyway, so I think it was Pluto and Pluto actually, and we can see all of these fragments flying into outer space. So these fragments are essentially the danger of the Kessler effect. So now many of these fragments may also collide with other objects and cause even more collisions and even more destruction. But as you see here, a lot of these objects will just kind of dissipate. They'll just kind of fly into either back into the black hole, which would be representative of our atmosphere, or not really smack into anything. So yes, Kessler effect is possible, and yes, we may experience collisions of different satellites, but at the same time, if I were to run this for a few more minutes and seconds, you'll realize and you'll notice that the collisions will not actually spread to other planets, other satellites. So here we have the fragments flying out, and none of them really hit anything. And we can double check that in a second. I'm gonna go into the chart right here and see if any of these fragments hit anything else. And you'll notice that it's probably not gonna hit anything. Now, maybe that's just a simulation in the game. Maybe, you know, maybe this is very simplified. Maybe there's just not enough satellites that I've added. I should have added like 1,000 for it to be more realistic. But that's not something my computer can handle. But at the same time, maybe Kessler effect is statistically improbable. Not impossible, improbable. Improbable means that it's very unlikely to occur. A collision is very probable, but a Kessler effect, where a domino effect essentially destroys the entirety of our satellites in orbit around Earth, is very improbable. So just for fun, let's go into the chart right here. And we're gonna zoom in on these planets and dwarf planets and see what's up. So here we have our wolves. None of the wolves changed, so none of the wolves had a collision. Let's look at the Pluto, and I think this is the Pluto that collided. So there are two Plutos that collided into each other. The other Plutos are fine. So there's quite a lot of Plutos we have. Quite a lot of it, may I add. And look, none of them have anything. You can actually, I can go through all of them, and this is kind of eerie actually. This is really creepy. But we can go through all of them and we'll notice that none of them have anything else. Their fragments are still flying around and not really causing any trouble to anyone. So okay, that's cool. Let's wait for another collision. Let's see what else happens. And after just half a day, there's another collision somewhere. I can't really see where it is, but the game stopped. The game paused. That means there was another collision. So that's collision number 2. And we do have a little bit more fragments flying around. But I don't know if there's an actual domino effect yet. So we're just gonna see if this becomes a domino effect. We're gonna run this for at least 10 days until at least 5 collisions occur, so that we can actually guesstimate whether this is a domino effect or just a random singular collision that is not going to cause any more damage. After 5.9 days, there's another third collision right there. You can see the fragments flying everywhere. So this is 3 collisions after about 6 days, which is obviously not representative of real life. Another collision, I think. There we go, another collision right here. 6 point something days. And number 5. So this is 5 collisions within 6.12 days. And the fragments are all concentrated right here in the middle. And this would represent the lower Earth orbit, where essentially most of the satellites are located anyway. But at the same time, this is the area where it's really easy to get rid of the fragments because there's a bit of atmosphere here. So the satellites would actually, or not the satellites, but the fragments would slow themselves down and crash back into the Earth atmosphere. So having fragments here is not a big deal. Having fragments on the outskirts is a really big deal. And another number 6 collision right here in the middle. This is all happening in the lower Earth orbit, or equivalent of it in this simulation. So we have 6 collisions after almost 7 days. And look at that, all of the fragments from that collision actually did fly into the outer orbital area, so the higher Earth orbit. And then this can be a problem because some of these fragments may actually smack into one of these satellites and then cause a runaway effect, also known as a domino effect. So let's just keep waiting. And I think this is a collision number 7 right here with Wolf. You can see something is going in. I'm assuming this is Pluto. Let's actually just watch this in slow motion if we can. And here we go. Something is going in. And I think this was a collision number 7. Alright, so 7 collisions so far. It's only been 7.8 days. And we still have about almost 3 days to go, or actually 2.3 days to go before we finish this simulation. So this is 7 collisions, and a lot of them created fragments, but none of them really created a massive amount of fragments that would cause something a little bit more dangerous, like a domino effect. Okay, here comes number 8. This is another Pluto colliding into something else. And we're already almost at 10 days, so there's only been 8 collisions, and you can see fragments flying around, orbiting the black hole. But interestingly, the collisions are not as frequent as they were when I just added the wolves. So I think now we've established some sort of equilibrium here, because the Plutos and the wolves are orbiting the black hole, but not really colliding into each other anymore. And you can see all of these fragments are relatively close to the actual black hole, so they're probably going to just get inside or get sucked into the black hole any second now. And here's number 9 collision. It's Wolf 359 with something else. I can't really tell what it is, but I'm going to guess that it's Pluto because it didn't increase its mass too much. And it's now 10 days, 10.1 days, but still only 9 collisions. You can see the remainders and fragments from the previous collisions flying around. And just to see if any other fragments collided with anything else, we're just going to go back into the chart. And what I'm going to do is I'm going to go individually through every single one of these wolves and also Plutos and see if their mass has changed, because this is how you can usually tell if a fragment has collided with something else. But we can see that the Plutos that had collisions, they're right here. They're all bright. The 5 of them are really bright, and their masses are different because they've encountered other Plutos. But all of these other Plutos, they haven't really changed in terms of mass. So this kind of gives you a visual representation of, you know, collisions and Kessler Effect, so, or maybe lack of Kessler Effect. So what I'm trying to say is that yes, collisions in space are possible, and it's very likely that at some point a satellite will collide into another satellite and will cause some destruction and possibly fragments flying into space. But at the same time, it looks like Kessler Effect will not cause a so-called dominoes effect. It will not cause more satellites to be destroyed. And yes, maybe this is just a very simplified simulation, but at the same time, because of this space and because of the distances involved, a fragment, even 100 fragments from a satellite are not going to cause gravity-like, I'm talking about the movie Gravity-like situation where suddenly everything gets destroyed and we have no more space program anywhere in the world. So I think that's my finding in this particular simulation. I think I'm going to say that despite a possibility for a collision, Kessler runaway effect may not occur, but I might be completely wrong because I just did not use enough satellites. So let's just clean up this mess. We're going to put another supermassive black hole. Let's instead turn this into a binary black hole system where both of these guys are going to orbit each other very nicely, and then we'll get to just observe them destroy everything in their path. How is that for science? There we go. All right, and begin. All right, now that looks much better. So here we go. Lots of collisions. That's because things are suddenly colliding into these black holes. In one of the previous videos, I demonstrated that if you have a binary system, be it a solar system or a black hole system, the orbits around those two objects will suddenly become very unstable. So here, what will very likely happen is things will fly out into the outer system or collide with my two binary black holes. And now this is the end of the Kessler system, yay or nay. But here we go. So they have nothing else orbiting around them. Everything else flew away. And we now have a binary black hole system with almost nothing around it. But obviously, if I really wanted to clean this mass up, all I had to do is just add a few zeros right here in the mass. And there we go. This is suddenly a mega massive black hole that is just going to vacuum absolutely everything. Now I just changed this to 300 masses of Milky Way, and this is what's happening. Basically, it's literally sucking everything in like a vacuum cleaner. Everything is just falling into this black hole to never be seen again. And look at this beautiful effect. It would obviously not be like this in real life because you would not be able to see anything as soon as it reaches the event horizon, but you would definitely see something though. There is going to be some kind of a halo-like effect, something similar to what we observe in the movie called Interstellar. Unfortunately, we can't really we can't do the same here, but you know, this is the best we can do. There's still some objects flying around, so let's just try to attract the rest of them as well. And I just noticed some of them actually end up escaping at ridiculously high speeds. Like, look at that Pluto just go. A speed of, that is ridiculous, 2,000, over 2,000 speeds of light. Obviously impossible, but fun nonetheless. This guy's even faster, 4,500 speeds of light. Anyway, on this beautiful note, let's end this simulation. This is investigation of Kessler Effect and what it may mean to us as a planet and also to our satellites that orbit around us. In the next video, I'm going to show you something really cool using a black hole and many different satellites, but I don't want to spoil it yet. Just wait and see. Thank you guys for watching. Please subscribe and hopefully you enjoyed this video. Check out some of the other Universe Sandbox 2 videos or Kerbal Space Program videos that I posted. But also don't forget to post what you think about Kessler Effect. Do you think it's real? Do you think it will actually destroy all satellites around our planet? Or do you think it's very unlikely to occur, just like I demonstrated in this simulation? Thank you, and game you later. Bye-bye.